Welcome everyone. Got a review here on our calculations for acceleration and free fall. You should be at a spot where if you were in class, this is complete, but I didn't think it would hurt to go over it again kind of quickly. If you've got specific questions, just let me know, and then maybe go through an example or two that I've seen historically trips kids up. So looking at this, these are the formulas that we should, be accountable for. You don't have to memorize these, and this is your little cheat sheet you can use on the quiz. This works for acceleration, for time, for velocity, for distance as well. With the term part here, I think you're at a spot where, you know what, actually I'm going to jump over and do the abbreviations first. We should know what A is, T, V, D, G, and then this last one here, triangle or delta. So when we look at lowercase a or t or v or d or g, I mean, these are all pretty clear cut, right? As far as the terminology that we've been using. When we get further into the course, we'll see that there's some goofy ones like, P is momentum or Q is specific heat. Keep in mind that not everything was formed in English language. But I digress. Let's get back to this here. So A is, of course, acceleration. T is time. V is velocity. And like our last quiz, I'm just going to kind of put in parentheses here speed. I know that velocities, magnitude and direction, or speed and direction, but we can use those interchangeably when we're working through our problems or our calculations. D is going to be distance. G is gravity. And then remember the delta or the triangle, it means changing. So with acceleration, we're primarily looking for the unit, or how we're measuring it, as meters per second squared. I don't think I put anything on this particular practice or quiz where it's like kilometers per hour squared for like your rate of acceleration. So let's just stick with this, and we'll describe it a bit more. But keep in mind that this squared, we've got our meters per second per second. So how many meters per second are changing per second? That's your acceleration, right? From previous calculations, we've kind of worked this through, but it's random, right? You get your change in velocity over time. So for time, I mean, sure, you could use days or years or whatever, but let's just kind of stick to seconds and hours for this activity. Velocity, same thing here. There's a lot of ways you could measure it, but we're just sticking right now with meters per second, or occasionally kilometers per hour. Distance, we'll be using meters and kilometers. Gravity, all right, so I'm going to give you the value and the unit here. The acceleration due to gravity is 9.8 meters per second squared. So this value is what we'll always use for gravity. Objects are going to be accelerated towards the Earth's surface at a rate of 9.8 meters per second squared. So think of those meter sticks we were using in the car race lab. 9.8 of those per second is what the acceleration rate's going to be. Gravity doesn't care if it's a book or a golf ball or a bowling ball or a pen or a book bag. Everything gets accelerated towards the Earth's surface at that rate. With our change in here, I just wanted a little friendly reminder that that's what the delta V is, or if you're even saying triangle V, but that's change in. It's all right. So before I get too far, actually, let's add a little something to this. And I want to take a look at this, and we're going to use this formula. If you notice here, you got acceleration equals velocity over time, or acceleration equals the change in velocity over time. So we'll use this one. I'm going to just put use if 2 velocities. So if you've got two velocities given, then we have to figure out the change in velocity. And you might remember from lecture, we looked at this and kind of stretched out to say, hey, acceleration is the change in velocity over time. And when we talk about that, we've got v subscript f minus v subscript I, which really just means your final velocity minus your initial velocity. So I'm going to jump away from the metric world, and we'll just use like a miles per hour example. If I said I was cruising down the expressway at 70 miles per hour and I accelerated to 78 miles per hour to pass a vehicle. In that example, my final velocity was 78 miles per hour. My initial was the 70. So you got that change in velocity. What's the difference there? And that's looking at what the change in velocity is over time. So we've got these guys here that hopefully you're getting a little bit more familiar with. And we can use them to calculate some of our practice. So historically here, there's been a couple that I've seen kids mess up on. And if you've been in class, there's a real good chance by now you've seen all these examples. Full key is posted on my site. But let's, since we're just kind of talking about this change in velocity, let's take a look at number 6. And I'll show you how I'd set this up. So remember, my first suggestion is always read through the problem. So we got Beavis cruising down I-96 at 30 meters per second, and he's coming up on another vehicle. He speeds up to 35 meters per second, and this takes him 1.5 seconds. At what rate did he accelerate? Okay, so mentally I'm thinking, guy's cruising down, speeds up to pass. It took him 1.5 seconds. Check. So my second step, I want to fill in all these givens. So I go down. All right, it's great. It's I-96, but it doesn't really matter. So I got 30 meters per second. That's an example of velocity. If you weren't aware of that, or you're like, Cash, it doesn't come out here and just tell me that's velocity. Well, use your crutch, right? I mean, units for that. That's an example of velocity. So it has to be measured in there. Just like if I've said, oh man, I got to hurry up here. I've only got 20 pounds left in class. That doesn't make any sense. We've got, pounds, not for a unit of measurement on time. So if I keep reading through this and I start to continue to organize here, I got 35 meters per second. So I've got this, and I could see where some kids would think, man, what's going on here? I got two velocities. Just trust the process here. Just continue to organize, right? So we keep going here. I've got 1.5 seconds. And at what rate does he accelerate? So I'm looking for that, right? Okay, so now I got to find my formula. That's an A equals. Okay, I can go back to my little cheat sheet formulas. Remember, if I've got two velocities, this is the one I'm using. So I've got my A equals change in V over T. So my change in velocity, remember my final velocity was the 35 meters per second. My initial velocity was the 30 meters per second. And all that took place over 1.5 seconds. So 35 was my final, 30 was my initial. The difference there is 5 meters per second. And that acceleration took place over 1.5 seconds. So I go to my calculator. I go 5 divided by 1.5. And I got that. So I'm just going to call that 3.33 repeating. Remember, match, that was a step. Solve, and then the last part, what's the unit? Well, if it was acceleration, and I don't recall, I can use my little cheat sheet to help me out with my units, but we know by now that that's the rate at which the acceleration took place, so it's ms squared. And I'm going to box off my answer so it's easy to see throughout all my work there. Okay, another problem, or type of problem I should say, that I've seen kids historically have problems with is like number 7 here. So step 1, right? trust the process. Read through the problem. Thomas drops an egg from his rooftop. Takes 2 seconds to hit the ground. What distance did the egg fall? All right, kid's on his rooftop, drops an egg, took 2 seconds, 1,000, 2, 1,000. How high was the rooftop? Let's figure this stuff out. Read it. Now I got to organize. Blah, blah, blah. 2 seconds. I know seconds is time, right? So 2.0 seconds. To hit the ground, what distance did the egg fall? So it looks like I'm solving for distance. Here's one of the hang-ups kids will have is they're like, there's nothing else in here, man. Well, remember, this is gravity. And we know what the value always is. It's a constant. Gravity always accelerates objects 9.8 meters per second squared. So I can plug in 9.8 meters per second squared for gravity. Check. So now I know I'm read through my problem. I've organized my stuff. I got to choose a formula, right? And it should be a formula that gives me distance. I can't just randomly select one here. So I got one formula here for distance, and it's d equals 1/2 gt squared. So this one looks a little intimidating to kids, but remember, we're just trusting the process here. Don't freak out when you see that if for some reason it's not familiar to you yet. We got a match. So our gravity was 9.8 times our time was 2 squared, and the half, I'm going to write this down as 0.5. Now, some of you with fancy calculators, you might be able to match up and enter everything in here just like this. I don't have a fancy calculator. I've got a little dollar store calculator. So this is how I'm going to set my stuff up. If you're wondering where I got this half is into 0.5, I guess I kind of jumped the gun there and just did that step for you. I know I got to enter half into my calculator as 0.5. So here's another problem that I've seen kids do. They'll multiply all this stuff together and then square the total. The only thing that's squared here is our time. So if I wanted to, I could enter this backwards. I could go 2 times 2, because it's squared, times 9.8 times 0.5. Or if you like to just kind of work stuff out and get it done, that's fine too. I could cross that out and just say, okay, well, that's really 4. So let's see what we got here. 0.5 times 9.8 times 4 equals, oops, sorry guys, I made a little boo-boo there. I got a 0.5 times 9.8 times 4, and we got 19.6. All right, well, now I'm at the point where I entered and solved. So I got 19.6. 19.6 what? We're in distance. So here's another thing that I've seen some kids make boo-boos on. They're like, all right, let me double check with this. Distance, is it meters? Is it kilometers? Gosh, there's so many things we can measure distance in. How do I select the right unit? This is why I encourage you to write the units with, each of your givens when you're organizing stuff. So then I can kind of say, what's the only example of distance or the only unit of distance in my givens? And hopefully you see it's meters. So I'd stick with meters. So, this was a house that we would measure almost 20 of those meter sticks that we had there. Relatively large, but kersplat. I'm sure that egg shattered. If you've got specific questions, let me know. If not, hopefully that sheds some light on some of the trickier ones. As always, if you need something, reach out via email or see me in class. Till we meet again, take care.